Okay, put your forefinger into the screen like this, all of you. Okay, this middle finger will be in the direction of the current. Put your left hand forefinger into the board, into the screen like this. Okay, this left hand middle finger will be pointing towards our right. Okay, forefinger, sorry, thumb will be pointing upwards. Thumb will be pointing upwards. That is, the force dF on every segment of the wire will be acting vertically upwards like this dF. This dF, this dF, this dF constitutes a resultant force on the wire. Okay, resultant force F on the wire. Okay, right? So this force will be acting perpendicular to both L and B. Perpendicular to both L and B. Because whenever we talk about cross product, okay, the resultant is always perpendicular to both the vectors, means plane containing, right, L and B, right? Here in this, we have not taken B in the direction of the plane. In the plane, we have taken what you call perpendicular to the plane. B itself is perpendicular to the plane. So force will be in the plane. Okay, perpendicular to the direction of current. Okay, this is what we have seen in our last class. Okay, force on a current carrying wire. ILV sin theta. Okay. I is given, L is given, B is given. Okay, find the force. Simply I into L into B into sin theta, whatever direction it is. Okay, right now, the next topic is we see what is known as velocity selector. Okay, put a subheading, velocity selector. Velocity selector. Okay, now consider a chamber like this with a small opening at the center. Okay, from here, let you send one charged particle. Okay, charge Q of mass M moving with a velocity V or different velocities, say V1, V2, V3, V4, like this. Okay, any velocities, any particle. Okay, some all are having same charge, same mass, but they are having different velocities. Now, in this region, put one plates like this, metal plates, and one region of magnetic field also, like this. Draw this figure. Now, in this region, there is a uniform magnetic field. There is a uniform magnetic field pointing into the board like this. Circular region. Of course, I'm drawing somewhat outside also. It doesn't matter. Magnetic field B is pointing. Please draw this figure. Okay, this uniform magnetic field is pointing into the board. Particle is coming straight, pointing into the board. Particle is coming like this. Yeah. So make this one positive, this plate negative. Connect them to some battery like this. Okay, positive, negative. Okay. Now what will happen whenever a charge Q enters into a uniform electric field, it experiences a force given by F equal to QE bar, we have seen. That force will be in the direction of the electric field for positive charge. Okay, similarly, whenever a charge Q enters into a uniform magnetic field, it experiences, this is electric force, this is magnetic force. Okay, this is magnetic force, FB equal to, right, Q into V bar cross B bar. V bar cross V bar. Okay, right? But in this region, both electric field and magnetic field are acting simultaneously. Okay, simultaneously. Now what will happen? Whenever a charge Q enters into this region, this is known as velocity selector region. Okay, this region itself, this region box is called velocity selector region or velocity selector box. Here what happens is, now what will happen, tell me, if this is a positive charge, say, what is true for positive charge will be true for negative charge also with opposite sign, that's all. Okay, so whenever a charge enters into uniform, a positive charge enters into a uniform electric field, it experiences a force given by F equal to QE bar. That electric field will be acting in which direction, right? Positive charge particle gets attracted towards negative charge. So the electric field direction will be towards our right like this. F electric field will be acting like this. Okay. Right now, what is the direction in which the force, magnetic force will act? Magnetic field is also acting now. So magnetic field also will exert some force because charge particle has some charge, particle is moving with some velocity v. Q into v cross v force also will come. What is the direction of the magnetic force? Okay, put your left hand forefinger in the direction of the field. Again, put it pointing into the screen, all of you. Okay, unless you put, you won't understand. Okay, put your left hand forefinger into the screen like this. Okay, right now what is happening? Particle is moving downwards. Particle is moving downwards means middle finger should be in the direction of the velocity. Means you should not change only the finger direction. You have to rotate your entire wrist and put it this way. Okay, such that the entire hand should, or the wrist should rotate. Okay, these directions should be fixed like this. Okay, you cannot change the orientation of your fingers. Put forefinger in the direction of the field that is pointing into the screen. All of you can do that. Okay, right now middle finger should be in the direction of motion of the particle. Means for this finger should move downwards because particle is moving downwards like this. Then force due to magnetic field will be acting towards our right. Towards our right. Okay, we should apply electric and magnetic fields in such a way such that they act in opposite directions. Means you should make this one negative. Okay, better. Yeah, this one negative and this one positive. Positive, negative. Okay, now force due to electric field will be acting. We should apply force, we should apply electric field such that it acts towards left. Okay, force due to electric field Fe will be acting towards our left. That's how we have to apply. Force due to magnetic field will be acting towards our right. Means now electric and magnetic forces are acting right in opposite directions to each other. Okay, when so particles are having some velocity, no, right? And some magnetic force will act, some electric force will act. They are not equal. So if depending on the velocity, Fb will depend on the velocity of the particle also. Depending on the velocity, some magnetic force will act, and that is say more than electric field. Okay, it will get deflected towards right. Okay, particles is depending on their velocity. If magnetic force is less than the electric force, they'll get deflected towards our left like this. Whichever force dominates on that particle, okay, right, that particle will get deflected in the direction of that force. Okay, but there will be some particles which are moving with exactly the right amount of velocity, where the leftwards acting electric force will be equal to the rightward acting magnetic force. Okay, such that when the magnitude QE bar, okay, the resultant force acting QE bar is equal to Q plus Q into, right, V bar cross V bar, the resultant force acting on the particles. Okay, when the resultant force is 0, that is QE bar equal to, right, minus Q into, right, V bar cross V bar equal to minus Q into V bar cross V bar. What will happen? The two forces are equal in magnitude, opposite in directions. Then the resultant force on the particle will be 0. The particle will be moving straight like this, undeflected. Okay, particle moves straight like this, right, undeflected. And there is a small opening exactly in the opposite direction. Okay, very extremely small hole, okay, will be present in exactly opposite to this entry point. There will be a small hole, very small hole. Okay, those particles only with that specific velocity. Okay, that specific velocity, right, will be undeflected, and they'll travel straight, okay, in that region and come out of this narrow hole. Means all the particles which are coming out of this narrow hole will have one specific velocity. Okay, how much is that velocity? Right, this q and q gets cancelled. This is nothing but minus vb. Okay, because v and b are perpendicular to each other. Vb sine theta sine 90 equal to 1. So electric field E equal to E bar equal to minus V bar, or V equal to, okay, E bar by B bar, E bar by B bar with minus sign. Okay, that only shows the direction. Okay, it will give us the direction. Okay, so remember E by B, electric field unit by magnetic field unit, will have direction. Sorry, the units of meters per second, because wherever E by B comes, okay, remember that will have the units. You can substitute here. Electric field is volt per meter or joule per coulomb. V equal to Weber per meter square. Okay, right? Simplify that, you will get meter per second. So E by B are having the units of meter per second. It denotes velocity. Okay, means all the particles with that specific velocity in the particles. So here I am sending particles with all possible velocities. Particles with one specific velocity will be able to come out of that region undeflected like this. That's why, because only particles with specific velocity can pass through this region and come out of this hole undeflected, this region is called velocity selector region. Now, I know, see, it is where do we use actually in isotope separation, people use this technique. Okay, mass spectroscopy. Suppose I'll take some material and I'll heat it, I'll produce, right, so particles with all possible velocities. Okay, all particles, suppose I'm producing alpha particles. Okay, alpha particles, see, charge and mass will be same. Q by m ratio of the particle will be same, but they come out with different velocities. They come out with different velocities. So I'll see to it that only particles with specific velocity, that depends on E and B. Of course, this minus sign indicates direction only. Forget about magnitude is equal to E by B. Only those particles with velocity V equal to E by B exactly will be able to pass out of this what's called region and come out. Now I'll put another what's called, this is known as Aston's mass spectrograph. Okay, in nuclear physics. Okay, I'll see to it that so these particles will will enter into another region B. So what happens? Radius R equal to mv by qb. R equal to mv by qb. All particles have same velocity. All particles have same charge. All particles are entering into same v dash. The particles with the different masses. Okay, particles with different masses will get deflected into radii of different circles of radii, different radii, and they will get deflected and fall separately like this. Means this technique is used to separate isotopes. What are isotopes? Isotopes are having same charge, okay, but different masses. Z is same, but mass is different. They are known as isotopes. Okay, charge, not alpha particles, sorry. Some isotopes are there. Isotopes, we make them ions. Okay, suppose calcium has 6 stable isotopes. So what do? I'll make calcium ions and make those calcium ions pass through this region. So all particles, all calcium ions, they have same charge, ion. Charge is same, but different isotopes have different masses. So they'll travel in circles of different radii and they'll go and fall on a plate like this. Okay, particles with the different masses will go and fall at different points on this scale. Now, at what distance they are falling, what is the radius of the circular path, I can find out what is the mass of the particle, which isotope it is. Depending on how many spots I get here, okay, that many isotopes, okay, or how, depending on the number of isotopes present, that many spots will come here. Okay, so immediately I can see, okay, how many isotopes are present in that B, like that. Okay, mass spectrographs we call it. Okay, this region is called velocity selector region. Okay, what is important is E by B has units of velocity. Okay, next one, particles with specific velocity, which is equal to E by B, that I can decide. Now you and I can decide how much should be that velocity. So it doesn't matter. Okay, particles will come out with same velocity. I'll see to it that they enter into another magnetic field. That magnetic field will bend the particles path into circles, but circles radius depends on the mass here. The higher the mass, the higher will be the radius. Okay, so heaviest isotope will fall here, lightest isotope will fall here. Like that, we can separate isotopes because isotopes can be separated only with mass variation. See, all isotopes have same charge. Same charge means same number of protons. Same number of protons means same number of electrons revolving around the nucleus. Means their chemical properties, optical properties will remain same. Then how do I differentiate or how do I separate isotopes? Only based on their mass. Okay, so right, charge is same, velocity is also same. The only difference will be mass. So according to mass, they get automatically separated. Okay, this is one earliest technique of separating isotopes in a given sample. Okay, this region is known as elastic selector region. So this is what about the magnetic field and electric field applications. Now we enter into what is known as Biot Savart Law. Okay, put a subheading bio. Okay, actually, though there are T's, say Biot Savart Law, people say T is silent in both. Okay, Biot Savart Law, because Biot Savart Law, that's how it should be pronounced. Okay, Biot Savart. Now, whenever there is some current in a wire, it produces magnetic field. That was discovered by this scientist, tell me. Okay, whenever there is a magnetic field, sorry, whenever there is some current in a wire like this, it produces magnetic field. That was discovered by one scientist. Current carrying wires produce magnetic field. Okay, was discovered by a scientist. Who is that? Can anybody tell me? Can anybody tell me? This scientist has discovered that current carrying wires produce magnetic field. A scientist called Oersted. Okay, Oersted is the first scientist to find out that current carrying wires produce magnetic field. Okay, when he was doing experiment with some dead frogs. Okay, whenever he's touching what you call something happened. Okay, so that's how we found that whenever there is some current in a wire, it produces magnetic field around it. That magnetic field lines are concentric circles. That magnetic field lines are concentric circles around the current carrying wire. Okay, that's what has been found. Means how do you find the direction of the magnetic field? If the wire is like this, okay, this is known as Ampere's law. Okay, Ampere's right hand rule. Okay, whenever there is some current in a wire like this in the direction, okay, hold the current carrying wire in your right hand with thumb in the direction of the current. Okay, curling right hand 4 fingers will give you direction of the magnetic field. Means magnetic field directions will be like this. Okay, please watch the video. Okay, magnetic field lines will be like this. Okay, clockwise this way. For current, direction of current like this. Because Ampere said that hold the current carrying wire in your right hand with thumb in the direction of current. Okay, don't hold any current wire. Okay, forget about Ampere, forget the direction of the magnetic field. If you hold a current carrying wire in right hand, what will happen? Okay, you will not exist. Okay, so let Ampere catch that current carrying wire. You find out the magnetic field. So here also there is some current carrying wire of some arbitrary shape. Okay, it will also produce magnetic field. The magnetic field will be concentric circles everywhere, right? Perpendicular to the direction of current like this. Now, what is the amount of magnetic field present at a point P, which is at a distance R from the wire? I want that. Okay, right, which is at a distance R from the wire. So what they did is they have taken a small element of length dl like this, some element of length dl, carrying of course current I, carrying current I. Okay, right, now at a point P, which is at a distance R from the wire. Okay, which is at a distance R from the wire. What is the magnetic field? What is the magnetic field? Okay, right, means this is also like Coulomb's law and universal law of gravitation by Newton. This is also experiment. This was also experimentally observed and stated law. Okay, right, what they found is the magnetic field due to the small element of length dl. Okay, small element of length dl, let us call it as db. db bar is found to be proportional to Just we don't need a Biot Savart law or Biot Savart to find out. With our common sense also, we can find out on what factors magnetic field depends. Okay, just tell me on what factors, how much will be the magnetic field depends on what factors you tell me. Okay, as much as possible, we will also try to become Biot Savart. Okay, first point will be, tell me how much will be the magnetic field here. Okay, depends on what factors. Tell me proportional to. Of course, equal to means you need to go into Biot Savart because you cannot do the experiment and find. But common sense says what? How much will be the magnetic field depends on. First thing depends on. Tell me whether.
Current in the wire.
Exactly. Okay. More the current, more will be the magnetic field. Less current, less will be the magnetic field. So it is proportional to I. And similarly, proportional to DL also, length of the element you are considering. You consider an infinitesimally small element, small magnetic field will present. You consider a bigger element, okay, more magnetic field will be present. So it is proportional to DL also. And what they have observed is, it is inversely proportional to square of the distance between that current element and the distance. Okay, and the point P. Okay, square of the distance. Of course, this as R keeps on increasing, B keeps on decreasing, that common sense is. Whether it is whether it decreases as 1 by R or 1 by R square or 1 by R cube, that depend, that of course they have found experimentally. Okay, so dB is found to be proportional to IDL and R square. One more thing, what they have observed, it is this we cannot guess. Okay, it is proportional to sine of the angle between the current element and this radius vector. Okay, proportional to sine theta. Okay, write down. Draw this figure and then write down. Okay, consider a small element of length dl. Small element of length dl. Okay, carrying a current I. The angle between I and dl will be in the direction of current only. Okay, IDL sine theta by r square. This is known as Biot Savart law. Okay, dB is proportional to IDL sine theta by r square. Okay, experimental observation has given them mod dB bar equal to, okay, mod dB bar equal to the proportionality sign. When it is replaced with a constant, the constant should be mu naught by 4 pi IDL sine theta by r square. Ideal sine theta by r square. This is known as Biot Savart law. This is known as Biot Savart law. Okay. Now, in vector notation, how do you write? With magnitude also I want. Not only, sorry, with the direction also. Not only magnitude, I need direction also. The dB bar equal to mu naught I by 4 pi. Mu naught I by 4 pi. Okay, DL bar cross R bar. Okay, DL bar cross R bar by R cube. Okay, where R bar is position vector of that point P from the element. Okay, that is R into R cap. Okay, what R bar position vector of that point P from the current element. Okay, that is nothing but its magnitude. Actual distance is R into, right, unit vector in the direction of the current. Unit vector, sorry, in the direction of R. So if you replace this R bar with R into R cap, one R and one R get cancelled. So simply, and DL bar cross R bar means DL R sine theta. R bar is nothing but R into R cap. One R over R gets cancelled. DL sine theta by R square only will remain. That direction, magnetic field will be like this. Means what? Magnetic field perpendicular to both DL, which is like this, and R like this. Okay, so close your right hand four fingers from DL to R. That magnetic field pointing right like this. Okay, close your right hand four fingers from DL to R. Cross product I told no. Okay, magnetic field is pointing into the board. Now hold this wire also like this. Hold this wire like this. Okay, with your right hand in this direction. Okay, with thumb in the direction of current. Right hand four fingers are curling out like this. Means what? Here, the magnetic lines of force will start like this. and at this point they'll go into the board. Okay, into the board. So Ampere's right hand rule gives like this, and dl bar cross r bar also gives the same. Magnetic field will pointing into the board, because suppose a straight wire is like this, when current is upwards, hold the wire like this. Okay, what is happening here? The fingers are coming out from this side. Okay, when you close your right hand four fingers, one side fingers are going into the board. Okay, into the board from me. Other side fingers are coming out of the board. Here, when you hold the right wire like this, okay, right, what is happening? Towards the right of the wire, fingers are pointing into the board. Means magnetic field will be going into the board here. Okay, here magnetic field will come out because fingers are coming out for this direction of current. Means there will be concentric circles like this. Okay, in this way. In this way. So towards our right, magnetic field is pointing into the board. Right here towards our left, magnetic field is pointing out of the board, because we are seeing in two-dimensional way. In three-dimensional, they are actually circles like this. They are circles like this. Okay. So how much will be the magnetic field? Means they have taken for a small element and they have calculated dB for that small element of length dl. Now what is the total field due to the entire wire? Okay, total field due to the entire wire is obtained by integrating this formula. Okay, integrating this formula. What is that? V bar equal to, right, integral dB bar. Integral dB bar equal to, right, mu naught I by 4 pi, mu naught I by 4 pi, right, integral dl bar cross r bar, dl bar cross r bar by r cube. Okay, with what you call that gives you the total magnetic field due to the entire wire. Okay, now this is Biot Savart Law. So we can find out for what amount of current in what type of wire, okay, how much will be the magnetic field at so and so distance. Now we will get it out. Why those fellows, Biot and Savart, they have not integrated themselves and have given the result finally. Okay, just like Newton did, just like what's called Coulomb did. They said that the force between two charges separated by distance will be equal to, will be proportional to Q1, Q2 R square, 1 by 4 pi epsilon Q1, Q2 R square. Biot Savart Law did not give us magnetic field like that. They have simply given current field due to a small element of length dl only. And you want the total field due to the entire wire. Means what they said is you integrate yourself. Okay, why did they give what you call this integration? Why did not they integrate and have given us? Tell me. Because they must not be knowing. They might not be knowing integration. Okay, experimentally they came up to this point, but they don't know integration. Maybe they are not knowing, they were not knowing integration, so they have asked us to integrate ourselves. Is it the case? Is it the case? Or is it why they have not given the magnetic logical that they have not done the integration? Maybe they are not knowing magnetic integration. In those days, there is no rule. Okay, integration differentiation came out, they got developed in 1880s, 1890s only. Okay, physicists have developed this integration differentiation concepts so that they are useful. Okay, they are not knowing, say, people in 1980s, sorry, 1850s, 1840s, 1860s, they don't know integration and differentiation. Calculus was not there. Slowly it got developed. And all are not proficient in calculus. Is that the case that they don't know, they were not knowing integration, so they are asking us to integrate? Is it the case, or is there any, there could be any other reason? Just guess. Because why they have not integrated this? Integration depends on the shape of the wire. Okay, a wire may be straight like this, or wire may be bent like this, or wire may be in a circular path, or wire may be in a semicircular path like this. Okay, in different cases, integration path will keep on, will be changing. So what this, they have given us the basic fundamental formula. Depending on your wire, the shape of the wire and length of the wire, you integrate yourself. That's why they have left this integration. Okay, so depending on the shape of the wire and the length of the wire, okay, we'll have to see how many different cases will come. Maybe have a current carrying wire, maybe in the form of a triangle like this. Okay, current carrying wire maybe in a circular loop like this, or it may be a straight line. Okay, it may be a semicircular path like this. We don't know, no. So what is the magnetic field at this point? Okay, shapes are different here in different cases. Okay, so that's why they said depending on your shape of your wire, you integrate yourself. Okay, so depending on different shapes, now we have to see what are the possible cases. First one is the field due to, okay, straight current carrying wire. Field due to straight current carrying wire. That becomes the first application of Biot Savart Law. Okay, B bar due to, write down applications. B due to, B due to a thin, comma, long, okay, straight wire. B due to a thin, long, straight wire. This is the first application. So consider some wire. Okay. Consider a straight wire like this. Straight wire like this. Say from point A to a point B. Okay. This is at a perpendicular distance. At a perpendicular distance. Or at a point P. What is the magnetic field if this wire carries a current I like this? Okay. Now, if right direction of magnetic field can be obtained from Ampere's rule. Okay, what is Ampere's rule? Hold the wire in your right hand. Okay, with thumb in the direction of the current. Curling right hand 4 fingers will give you direction of the magnetic field. So magnetic field at point P will be pointing into the board. Okay, because we have taken the right of the wire. Okay, if you take this point P here, okay, our 4 fingers will be curling out and coming out like this from left side. So magnetic field pointing out of the board here, it will pointing into the board here. So that's why I put one cross mark there. How much is that magnetic field? How much is that magnetic field means the distance is C, perpendicular distances are. Earlier in Biot Savart Law, it is the actual distance between the current element and the point P. That we have taken as R. But here it is the perpendicular distance from the wire. And one more thing, because of the sine theta factor, remember, whenever sine theta comes into the picture, whenever DL and I are in the same direction, okay, the magnetic field will be 0. DL bar cross R bar, no. DL bar cross R bar, if DL and R are in the same direction, means if the wire is like this and you want to find out magnetic field here, so DL also is like this. Okay, R is also like this. If DL and R are in the same direction, okay, field will be 0. So remember, whenever sine theta factor comes into picture, in the direction of, okay, DL and R, if R and DL are in the same direction, magnetic field will be 0. Means whenever there is some wire here, okay, in the direction of the wire, in the front of the wire and at the back of the wire also, magnetic field will be 0. So magnetic field will be only perpendicular to maximum magnetic field will be there perpendicular to the wire. Okay, R and DL, wire length and DL and R should not be in the same direction. Okay, in the perpendicular direction only magnetic field will be active. Right, so here the magnetic lines of force will be like this. The magnetic lines of force will be concentric circles like this. Something like this. Okay, right? The direction will be in this direction. The direction will be like this. Now, what is the magnetic field here? As said by Biot Savart Law, we have to consider a small element of length dl. Okay. Now, this be the line joining. this is say some distance x. Earlier, this was r in Biot Savart Law. Now r is the perpendicular distance, so I'm taking this as x. So this element subtends a small angle d theta here. Okay, right? And this angle is some theta here, some theta here. Okay, so I'll find out what you call the field due to the small element of length dl, and then I'll integrate it from the total length a to b. A makes an angle. Integration means from where to where. A makes an angle. A subtends an angle theta 1, and B, the end point, subtends an angle theta 2, like this. This angle is theta 2. This angle is theta 1. Say. Okay, or this angle is alpha 1. Okay, this angle is alpha 2. Here I have taken a small element. Okay, this angle is theta 2. So here we have considered a small element of length dl which subtends an angle, arbitrary angle theta. And this is d theta. Okay, right? This subtends an angle theta. Say this is d theta. So angle d theta equal to arc length by radius we call, and this be x. Say this be x. Draw this figure. You find out dv bar equal to idl sine theta by r square. Okay, mu naught by 4 pi dl sine theta by r square, and integrate it from theta 1 to theta 2. What do you get? Okay, I'm not giving the integration. I'm directly giving you the result. Okay, right? What is that? B bar equal to, directly write out. Okay, B bar equal to mu naught I by 4 pi r into cos theta 1 minus cos theta 2. So in terms of this theta 1 and theta 2, okay, mu naught I by 4 pi r into cos theta 1 minus cos theta 2. You can solve the integration from in terms of alpha and alpha 2 also. Okay, if you do that in terms of alpha 1 and alpha 2, mu naught I by 4 pi r into, don't bother about integration, sine alpha 1 plus, okay, sine alpha 1 plus sine alpha 2. Sine alpha 2. Okay, either you can use this formula, but this is more popular. Okay, mu naught I by 4 pi r into cos theta 1 minus cos theta 2. This is a general formula for any wire, okay, of length L, okay, whose endpoints subtend angles theta 1 and theta 2 at a distance, perpendicular distance r from the wire. Remember, this r is the perpendicular distance from the wire. I is current in the wire. Okay, now first special case we will see now today. Okay, first special case, case one of infinitely long wire. Infinitely long wire. Infinitely long wire. Consider the length of the wire to be infinity. When length of the wire is infinity, what will happen? This will go up to minus infinity. Okay, as this length keeps on increasing to minus infinity, what will happen to the angle here? Earlier, when the length is up to this point, it is theta 1. Now, when I extend the length to this one, that theta decreases. When this goes to, theta keeps on decreasing. When I go to minus infinity, the theta will be almost how much? 0 degrees. Okay, theta will be almost 0. Means due to an infinitely long wire, like, due to an infinitely long wire like this, okay, at this point, okay, this theta keeps on decreasing now. This theta keeps on decreasing like this. Okay, the wire is really infinitely long. Okay, this theta tends to 0. Similarly, what happens to this point? Tell me. Okay, this angle, wire is like this. This is up to point B. This is our angle theta. Okay, when the point is B is here. Okay, I have to write like this. This theta value will keep on increasing. When the wire is really infinitely long, okay, when B goes to infinity, when this B goes to infinity, right, what will happen? This theta will be like this. Means theta will keep on increasing. When really B goes to infinity, theta becomes 180 degrees. So for an infinitely long wire, the situation is like this. Right down. For infinitely long wire, theta 1 equal to 0, theta 2 equal to pi. Okay, theta 2 equal to pi. Therefore, B equal to magnitude only. Okay, direction is given by Ampere's law. Mu naught I by 4 pi r into cos 0 is how much? 1 minus cos pi is how much? Minus 1. 1 minus of minus 1 is plus 1. Okay, this is nothing but mu naught I by 2 pi r. Okay, due to an infinitely long wire. Okay, magnetic field at a distance r. This result is very, very crucial. It comes at least 100 places. Okay, many places it comes. Mu naught I by 2 pi r. Remember this form. Mu naught value. Mu naught is permeability of free space. Mu naught value is 4 pi into 10 to the power minus 7 Henry per meter. Henry per meter. Okay, 4 pi to 10 to the power minus 7 Henry per meter is mu naught value. Depending on the current and depending on the perpendicular distance from wire, B keeps on changing. This is a very, very crucial result. Remember, okay, we'll be using this again, time and again, many places. B due to a thin, long, straight wire. Okay, right now, do we really have infinite wires? Need not be. Wire may be of 1 meter length or 10 meters length. If the distance from the wire is only hardly 1 millimeter, this 1 meter wire itself can be, this angle will be almost 0. No. This angle will be almost 180 degrees. This is not even 1 meter, hardly 10 centimeters, and the distance is half mm. Okay, this behaves like an infinite long wire only. If really the distance is 1 meter, it goes beyond this my screen, and you try to find out the magnetic field at a distance of just 1 mm from the surface of the wire. Okay, that 1 meter wire itself will become infinite wire. Really infinite means we don't have an infinitely long wire. Any wire, okay, when the distance between the wire and the point under consideration is very small, okay, that wire becomes an infinitely long wire. Okay, this is the first application. Okay, this is for general case of any limited wire, wire of any limited length. All that we need to know is we have to know theta 1 and theta 2. That is, what is the angle subtended by the end points in the direction of current, from the current direction, from I direction to that radius vectors, you have to draw angles. Okay, here current is in this direction, current is in this direction. From the direction of current to the radius vector, what is the angle subtended? Okay, right? That is, this is the most general case, and this is one special case of infinitely long wire. Okay, so I'll stop our class here. We'll continue tomorrow. Okay, tomorrow morning also the class will be at 6:30 or 6:15. Okay, please be ready for that. I'll send you the link by evening. Okay, right? We'll stop our class here. We'll continue tomorrow. Bye. Till then, bye everybody.
Thank you, sir.
Yeah.
Thank